Okay, continuation of Hall effects and testing them. I mentioned previously that we were going to skip past these flow charts in page 21, 22, 23. What I want to do is give you guys an overview of what I'm trying to show you in these flow charts and what it would look like, say, with a problem, starting with signal voltage measured at the sensor is fixed low. And so let's just put a generic picture up here. And this is pretty typical of wiring to a Hall effect. That, let's say this is our crank sensor. You got three wires, all three wires extending to the engine computer. They're not all like that. You can have some of them with an external power. But one of the things when you're dealing with a Hall effect, let's say the middle wire is our signal. Put a connector in here. Let's say that we are fixed at 0 volts. So we have a flat line on that signal. And what we want to have is a square wave, obviously. It is a Hall effect. It's a high-low, on-off digital signal. The process you would go through would be checking your power, checking your ground. So a review for the power is anywhere from 5 to 12 volts would be a power feed for a Hall effect. In the video that we watched on the Chrysler design, it was a 5-volt supplied power feed to that Hall effect. So on that particular design, that 5-volt power feed is really the reference circuit. It's the same circuit that is shared everywhere else. If you want to, you can refer to the 5-volt reference section I have, and it shows you the internals of how those are all connected. So that was the video that we watched, used a 5-volt supply. The ground, we said our ground, we need to be 100 millivolts or less. Less than 100 millivolts. But remember that we don't want to be cranking the engine when we're checking that number, because if you crank an engine over, you're going to have elevated ground voltages all over the car from that starter amperage that's loading the circuit. So 100 millivolts or less, that'd be key on engine off or key on engine run. So we're cranking the engine, we have 0 volts. Circuit design is everything here now. If you don't know the circuit design, it's going to be a little bit more difficult to troubleshoot it because of the variables that are there. Let's say that we know that this is a pull-down design. Now, you might be thinking, how do you know? Is there a way to know? In fact, one of you asked me yesterday, is there a way to know on a wiring diagram if it's pull-up or pull-down design? The answer on an electronic switch input is no. There is no way on a wiring diagram to electrically identify the circuit design. Was it possible on a mechanical and hydraulic, quote, switch input, section 2? It is possible. You look at the wire that does not go to the computer, always tells you what the circuit design is. But the problem with this one is there's no internals here. There's no internals here. How do you know what the circuit design is? You don't. So refer back to section 2. That's why I gave you a whole list of electronic designs as just a base. And of course, I told you guys you want to add to that. So again, I'm referring to section 2, electronic switch inputs. I even have a page that's designated how to identify an electronic switch input. So let's say in this scenario, again, we're trying to match this where it says pull down testing, signal voltage measured at the switch is fixed low. I'm going to tell you how I would handle this. I would simply, at this point right here, I would simply unplug that connector. On a pull-down design, what should my signal voltage do with the sensor unplugged? This signal voltage with the sensor unplugged, this should go to 5 volts. At least on a Chrysler design. Chrysler uses 5-volt pull-down designs for all of their Hall effects. Nice thing about Chrysler, they've been doing it that way for 30 years. You know, all the other manufacturers tend to change year to year, model to model, sensor to sensor, what they're using. You can have a 12-volt pull-up design Hall effect on the same car, have a 5-volt pull-down design. That kind of sucks, but that's the way it is. Chrysler's been uniform with theirs. I'm using that one because it's an easy one to talk about. If you disconnect this sensor and you got 5 volts, what was the problem? Why did you have 0 volts the whole time? Because the sensor is electrically shorted out, pulling the signal down all the time. Unplug it, goes to 5, you're done, you need a sensor. Okay? If you unplug that and it stays at 0, so you've unplugged the Hall effect sensor and the signal still at 0, you better not put a sensor in this car. It's a pull-down design. There should be voltage on this signal wire. It's not there. So now what do? What would be your next step? I'm thinking of next easiest step. At this point, we're going to have to measure it at the computer. If I read at the computer, same wire, 5 volts here, and I read 0 volts at the sensor, there's really only one possibility, and that is you have an open in that signal wire. Okay? If you go to the computer and you measure 0 volts at the computer, it cannot be an open in the signal wire. What we're dealing with is either a short to ground in that signal wire or a faulty computer. So how do we handle this one with a short to ground? Suggestion is to use the ohm meter. And I know that might be the first time you've heard me say that, to use the ohm meter. What we want to do to check this circuit, we need to isolate it. So we're going to need to disconnect it from the sensor, disconnect it from the computer. We have a totally isolated signal wire. That would be this one right here. Your signal wire is now isolated. And we're going to check this signal wire for a short to ground. Short to ground, take your ohm meter to one end of the wire and to a known good ground. The only acceptable reading here is OL M ohms. That's what you want to see. Well, technically, you'd want to see 0 here, because what this reading means is you have an engine computer problem. If you read 0 volts, that means you have a short to ground in the harness, and that would be preferable cost-wise, right? As far as the wire goes, though, we don't want to see 0 ohms, because 0 ohms means that that meter has found a path, and that would be a bad wire. Bad wire, bad computer. So if the wire shows you it's good, if you have this number, our focus goes toward this engine computer. Does that make sense? All right, what if, let's do this same scenario here. We're dealing with this same circuit, and let's say that we're fixed at 5 volts all the time, flat line 5 volts, no square wave. Same process. Check your power, check your ground. Let's say, and I don't know if I have this one in there, but let's say that your reference wire, that we have 0 volts on the reference circuit, is this. Yeah, that's probably not going to happen on this design, because if you had a shorted reference, you'd also not have 5 here either, because it uses that same circuit. The older designs, I'll give you that one. The older Chrysler designs didn't use 5 volts, they used a 9-volt reference. So it was a separate circuit. And that 9-volt ref actually fed the crank, it fed the cam, and it fed the vehicle speed sensor. And the scenario there, if you had 0 volts on the power feed to the Hall effect, and I have seen this, that a shorted vehicle speed sensor can pull this whole circuit down. Very similar to our 5-volt reference circuit, that one sensor shorts out, it pulls the whole circuit down. If the VSS is shorted, everything that is attached to my blue wire here is going to drop down to 0 volts. There'll be no voltage at the cam, no voltage at the VSS, no voltage at the crank. This vehicle will not start with a shorted vehicle speed sensor. Okay? So something to consider there. So let's go back, and we have a fixed 5-volt signal, which, by the way, that would happen with no power feed here. You'd have a fixed signal at 5. But excluding a bad power, say we have fixed 5 volts, we check our power, check our ground, it's good. How's my signal wire on the pull-down design? We're fixed at 5 volts. We already know that the computer is good and that the signal wire integrity from the computer to the sensor is good. How nice is that? Pull-down design. Where is our focus? It's the sensor itself, right? Or maybe we have a broken timing belt or something crazy where we have no motion. Of course, the signal is going to be fixed. So you're going to want to make sure that, you know, that reluctor is okay, whatever's driving this. In this case, what I would do is a bypass test just to make myself feel better. I want to see a reaction. And so I'm plugging in also for you guys, you know, I'm kind of going through this just a different way, but I'm plugging in page 26 too, this bypass test. How do you do it? What are we looking for? And when would we do it? So in this scenario, I would take a test light connected to battery negative, and I'm going to pull the signal to ground. Isn't that what the sensor does anyway? Why am I using a test light instead of a jumper wire? You can use a jumper wire. You will not hurt this sensor with a jumper wire. But if you use a jumper wire and you touch the wrong pin, you might cause some problems. So why are we using the test light? It's just a safer tool in case we do it wrong, right? Test light to ground, touch on and off the signal wire. What's the computer going to see on this circuit as you take that test light on and off? It's going to see a square wave. What is its response? What's its reaction? If this is a single ignition system where it only, not single ignition, but a single sensor, only one crank sensor, no cam, what do you think is going to happen? What's the reaction? Fuel pump's going to turn on. You're going to hear the injectors fire, and you're going to hear the and the ignition system is going to fire. You're going to get a spark. So that's the reaction you're looking for. If that happens, does that make you feel 100% confident that you're on the right track, that you need a crank sensor when you do this test? That's really what we're trying to do here, right? What if it's a system that needs both cam and crank signals at the same time? Are you going to have spark? Probably not. So what reaction are you looking for? Well, I showed you in that video on that Chrysler that we had a crank count that would increase every time I touched that circuit. In my book, on page 29, what we're looking at here is just some data PIDs that you can look at. So if you're doing a bypass test, you can look at the crank sensor data PID, and it should say yes. It's going to be no with the engine off. It should say yes as you're doing this bypass test. So that would be another example of a reaction you're looking for. Or maybe you see the RPM increase, which would be another data parameter that you can look at. But the point with this bypass test is it makes you feel 100% confident that you're on the right track and that you do, in fact, have a faulty crank sensor. Okay? So that should have covered, what I just did right there, should have covered this page. Sorry. Fixed high. Fixed low. Should have covered this page, page 21, and this page, 22. Pull-up testing. Let's do that one real quick. A pull-up design, a little bit different. This is typically what I see with a pull-up. I'm gonna make this externally sourced 12 volt. I'm not 100% sure on that. That 12 could still come from the engine computer. This is my crank sensor. This is the PCM. What I found with the pull-up designs, I don't know if I've ever seen a lower than 12-volt signal on a pull-up design. I'm pretty sure they're all 0-12, the signal. The difference, I think, with these two, you know what, just for argument, we won't do it that way. I'll just run all three to the computer, just like the other one. And I want you to understand on this design up here, with this disconnected, it is normal to see 5 volts on that signal wire. Okay? Pull down design, it's normal. On a pull up design, if you were to disconnect this, it is normal to see 0 volts on the signal wire. So we have to approach these differently. That would be the first thing to understand. Pull up design, crank signal is going to generate the square wave and send it to the computer in a pull up fashion. Computer's going to see a square wave just like the pull down, but a little bit different internal circuitry. So if we're fixed at 0 here, we can't just simply unplug the sensor step 1 and look for the voltage to go, say, to 12. It doesn't function that way. That test isn't going to help you. So what I would do on a pull up design Hall effect, and I'm not sure exactly what I have written in my flowchart. I'm just trying to think how I would go through it, and hopefully it matches. Fixed at 0 volts, so it's fixed low. What do we want to do next? Check your power, check your ground. Your power feed is going to be anywhere from 5 to 12, probably going to be 12 on a pull-up design. So let's say we got 12 volts on the feed. We have less than 100 millivolts on our ground. We crank the engine over. We're fixed at 0 on the signal. Probably a bad sensor at this point. That's where we're at. What I want to make sure, though, is that my signal wire isn't shorted to ground. And I want to make sure that my computer can respond to a changing signal. So what I'm going to do is disconnect the sensor. You might not have to disconnect the sensor. It depends on the design. Take my test light to battery positive. I'm going to create a signal that the sensor makes, a pull-up design circuit. If you take that test light to battery positive and touch on the signal, and let's say we're looking at, let's say it's a cam sensor. One video I have hyperlinked here, it is a cam sensor, and when I do this test, it says it goes from no to yes. What's that tell you about the integrity of the signal wire and the computer itself with this test? Tells you they're good, and our focus then is on the sensor. We're going to probably replace the sensor at that point. Very fast way to identify circuit integrity. Believe I have that. Pull up testing fixed low. Check for mechanical problems. Check your power and ground. Check the signal wire for a short to ground. What am I doing? How am I checking that? There's 2 ways I'm giving you. The bypass test right here is what we just did. That was our concern, right? We can use an ohm meter too. On the pull up, signal voltage measured at the switch is fixed high. I have to tell you, I don't think I've ever seen that. But the only thing that would cause that would be something with the reluctor. Something happened with that. I don't know if I've ever seen a Hall effect fixed high like that. I mean, it is possible. So I'm saying switch. See, I called this a switch. This would be more the sensor. Signal voltage measured at the switch. This is my Hall effect. My Hall effect switch in quotes. I should have had that maybe in quotes. Hall effect sensor, Hall effect switch. I said the sensor up here. I don't know why I called it a switch here. I apologize for that. Signal voltage measured at the switch, fixed low. Switch, because I'm thinking switch inputs. So again, what I'm referring to here, switch, is the Hall effect. So make sure you guys make that correction. This one is a little bit goofy. Page 25. What I'm saying is you have a trouble code set for the switch, right? Again, switch input in our case is our Hall effect. And when we come down to the sensor and do our checks, what we find at the sensor is we have a good square wave at the sensor. It's functioning, but yet we have a trouble code for it. On a pull-up design, it is possible that the signal wire is open. That's not possible on a pull-down design. On a pull-down design, the computer is the source. It's feeding it this way, and the switch pulls it to ground to make a square wave. So if you have a square wave at the sensor, you can't have an open in the signal wire. But a pull-up design is unique in that this can happen, that you have an open in the signal wire. So the symptom would be you have a code, you have a DTC in the computer for this sensor, but when you check the sensor, it's good. The next thing that you would want to do is check the same signal at the computer, and if you have a flat line at the computer and a square wave at the sensor, what's your problem? You have an open in that circuit. So that's what this page addresses. All right, let's move away from this. It's complicated to do the what if scenario. Guys, these pages are for you for a later time. You'll thank me for it someday when you're following these. Review of the bypass test, pull up, pull down. What do we do for a pull down? Test light to battery negative. What do we do for a pull up? Test light to battery positive. Something to consider when we're doing bypass tests is what is the response that you're looking for? What's the response? Well, the question for you is what is the sensor that you're trying to bypass? Will determine what response you're looking for. Okay? So injector pulse, scan data, PID changes, watch the instrument cluster, maybe see the tach flutter. And if we plug this into where we are, which is ignition inputs, basically we're talking about a cam and a crank sensor that we're doing bypass tests on. And what you need to remember is some systems need both signals at the same time for spark to take place. So if you're just doing a bypass test on the crank sensor, it might not be enough information on that system for the computer to fire the coil because it needs the cam at the same time. We talked a little bit about that. This bypass test is not foolproof. You know, on some systems, you're looking for a reaction, you're looking for a change, and you won't see one. I've seen vehicles that, unless there is a crank signal, an RPM signal on the crank, the scan tool will not update the cam data parameter. So you're doing bypass tests on the cam sensor only, and there's no reaction because there's no RPM signal, and the computer's not looking in that direction. Does that make sense? So in that case, you're not going to see the reaction you're looking for. There isn't one because the computer's looking for a crank. And there's no crank signal, so it's not going to update that cam. That is possible. You have to be careful with that. All right, let's finish this up. Here's where we're going next. Optical distributors.